All right. Today's discussion is Feynman diagrams. I apologize for the raspy voice, but we'll do the best we can here. So, Feynman developed a graphical representation of particle interactions you could use to predict the probabilities of the outcomes of particle collisions. So, this is a very simple technique with a lot of really profound and deep meaning in it. So, we have two axes, one is space and the other is time. Most often the time is written on the bottom, but not always, and I'll throw it in here just so you can see what it looks like. So IB generally puts time on the bottom. So these are interesting diagrams to look at, even though they're quite simple. They pack a lot of information in them, and there's a very elegant sophistication to them. So the first time you look at them, you just try and understand what you can. And then as you look at more of them, you start to dig a little deeper and you start to explore what all of the little parts mean. So do not think for an instant that you'll be an expert just by going through this once really quickly. It takes a little bit of figuring and going through and drawing and, okay, arguing with yourself and others. And that's all good stuff. So if we look at two electrons that are approaching each other, we know that because they have the same charge, when they approach each other, they're going to repel each other. And so it's that mechanism for why they repel that we're investigating. And in this case, that little mechanism is put in this little green circle here called the bubble of ignorance. And that doesn't mean that they don't know what's going on. It just means they have a theory, and one day that theory might be totally flipped on its head and changed. So there's a certain humbleness to saying we don't really know, but this is what we think, and just moving forward with it. So, and you can notice there's some arrows. Time ticks to the right here. So the two electrons come in, something happens, they're both repelled. It's not like a vector diagram where the angles mean anything. We won't read that deep into it. Okay, so the bubble of ignorance, as I said, that's the actual location that we're investigating. So there's a legend if you want to think of it that way. Particles are basically represented with straight arrows, just like we have here. The exchange force particles are represented with either wavy lines, so things like photons, W plus, W minus, and Z bosons. And you'll notice those two are same color and same symbol. And then lastly, gluons, which has this little green curly Q. And that's the strong nuclear. So the electromagnetic exchange particles and the weak exchange particles are actually linked together. So they've actually been combined into an electroweak force. So these are our three symbols. This is what we need to know. So this is what a diagram looks like. So this is the electron coming in. This is another electron coming in. You see an exchange here. And so if we look at that exchange particle, it's in the electroweak category. It's orange, it's squiggly, and it's a photon. So just like we did in class where we threw a ball while standing on a slider, or the boomerang analogy, that's what's happening. So there's an exchange particle which makes the electron change direction. Okay, if you just look at one half of it, it looks like this. And that's in its basics what a Feynman diagram is. And there's a lot of really subtle things that happen here, things that we'll read into. We'll use our conservation of baryon, lepton, charge, all of those things will come into play. So let's get into it. So this is probably the one thing that's going to cause people some problems. When you look at this graph here, that time moves to the right. So this is time ticking by. But when we represent antimatter, okay, the arrows are drawn backwards. This isn't to say that antimatter goes backwards in time. It's just the way they represent it with the relatively simple symbols they're using that make this solution quite interesting. Okay, so In comes a positron, in comes a positron. There's an exchange particles here in the photons, and then off they go in different directions. Okay, so it's just like an electron interaction, only we're using positrons. Okay, and again, the expectations of what you will be able to know and remember is I think fairly low. Just to pull these things out of the air is not something you would be expected to do, but we should learn how to read them and interpret some of the basics in it, and that's what I'm going to try and do today for you. So there's a photon traveling along, and it produces an electron-positron pair. Now, there's no real expectation that you would know that, but now that you've seen it, you go, that's interesting. And why would that be interesting? Well, one is an electron, and a positron, that's its antimatter. So we've talked about how things, when antimatter meets matter, it just creates energy. Well, the reverse is true. You can have energy that just turns into matter. Okay, but it'll be matter and antimatter together. And all of it follows some rules. So if we do a quick conservation check, let's look at the first one up here. So the charge on a photon is zero. Okay, it's not negative or positive, it's just zero. So if we check charge, it has a zero. The charge on an electron is negative. Charge on a positron is positive. It passes our charge conservation. If we look at baryon number, none of these things are baryons, so it passes baryon number. And then if we look at our lepton numbers, photon's not a lepton. Okay, it's just the exchange particle. But an electron and a positron, they would have a negative one and a positive one, lepton numbers. And again, it bounces. So this is a possible reaction. It's feasible. You could do the exact same thing in reverse. If you had an electron-positron pair annihilating to become a photon, just the numbers would flip on each side of the equal sign. This is an example where the axis has been flipped. So you can see time is going up the page. Okay, so the electrons are traveling along, they get close to each other. Here's the photon that's exchanged, the electrons move far away. And if you remember, virtual photon or virtual particle is something that has a fairly short range for its existence, but we'll talk more about that in a bit. So just notice that as time goes up, position is on the bottom. Still easy, it's fairly straightforward to read, but just be mindful of where the time value falls. Okay, so let's look at this one, because this one is the heart of a bunch of things we actually need to know. So here's a diagram of a down quark emitting a W minus particle that decays into an electron and an antineutrino. And you might remember what that is or what that's part of. If beta negative decay is dancing in your mind, then you're on the right track. So let's take a look. Here's the reaction up here. My down quark is turning into an up quark plus an electron plus an antineutrino electron. Okay, so if we do our conservation rules, the charge of a down quark, and this is why we have this fancy table. You can bring your table in. Okay, you look up a down quark, and it has a charge of negative 1/3. So let's do this really. Actually, let's just do the whole thing. Yeah, we'll do the big reaction, and then we'll look at smaller parts to it. So we have a negative 1/3 equals. Okay, so now I have an up quark, which is a charge of 2/3. And then the only way for those to balance is if the W boson here takes some negative, or is a negative charge, and it's a negative 1. So we're kind of looking at this interaction really right here. Oh, sorry, I got ahead of myself here. We're doing the whole thing. Let me pause on that thought for a minute. I'll come back to that in 1 second. So we're looking at this reaction. We'll do the whole reaction first, and then we'll look at the details. So we have a negative 1/3, a 2/3, and then if we look at the electron, that's a negative 1. And the neutrino is 0. And if you add those together and check, it passes charge. If we look at baryon number, a down quark has a baryon number of 1/3. An up quark has a baryon number of 1/3. And the other two are leptons, so they don't provide anything for that. If we look at the lepton for the big equation, It's going to be 0, 0, and then the electron would have a 1 and the negative 1. Better double check here. I'll be backwards, but they're opposites. Let me just double check before I get too far into this. Lepton number of an electron. Oops, I got them backwards. Positive 1. My bad. I'll blame the congestion. This is a positive, and this guy's the negative. But the point is that they still balance. Okay, so that overall big reaction up here, it passes conservation, baryon, and lepton. Okay, I'm going to just change to green for a minute. Now, if we just investigate this guy, and this is the piece that isn't explained very well in many books, if we just look at it from a charge perspective, a down quark has a charge of negative 1/3. Okay, and then it turns into an up quark, which is 2/3, and a W negative boson, and it has a charge of negative 1. And so when you're looking at that, this is really important, understanding the small pieces of these diagrams, is things still have to balance. So negative 1 is the same as 2/3 minus 1. And that's why this is a W minus boson and not a W plus, okay, or a Z0. So that interaction right there of what needs to balance the charge is what dictates whether this is W minus plus or Z0. Okay, so those are the little details. So there's the big picture, which was the big blue equation, and then there's little parts to it. And you could do another one down here if you wanted to. Okay, you'd have a negative 1 coming in. You'd have a 0 here, so negative 1 here. You'd have a 0 on the neutrino, and you'd have a negative 1 on the electron, and again, it would balance for charge. Alright, so let's take a look at this one. And again, I reiterate, you're not expected to know every single thing here. But some of them should kind of make sense as you kind of read and make connections. So if you notice up here, we have a DUU, so a down, up, up, and a down, up, up. So nothing's actually changed here, okay, but a gluon has been emitted. So if you remember, gluons only work with quarks, okay, so it's emitted a gluon, and then from the gluon, there's two quarks that have been created. Now, an anti-down and a down aren't going to exist for very long. They don't like being away from each other. So this will disintegrate very quickly. But just so you can see what a gluon exchange particle looks like. And again, there are limits on what the expectations of your knowledge are to be in terms of understanding. But if we can read that and kind of go, okay, I can kind of see where that comes from, that would be a win for me. Explain what has happened in this Feynman diagram. Now, we've actually just looked at this one already. So if we go back here for a minute, we had a down turning into an up with an electron and an anti-electron neutrino. Well, here's the rest of the story. Here's that down quark again. Here's the up quark. Well, an up, down, down, that's a neutron. And then the up, down, up, that's a proton. So this, this is a diagram of our beta negative decay. Okay, so if you take a minute, we looked at this smaller interaction. We can do the conservation check again down here. If I can get it to move up here. So if we looked at the overall conservation of the overall equation, you can go through a neutron is 0, proton, I got it backwards, proton is positive 1, neutron is or electron is negative 1, antineutrino is 0. If we carry on to baryon number, neutron and proton both have baryon numbers of 1, so it passes that. And then if we check the leptons, 0 and 0 for the neutron and proton, and the electron and the anti-electron neutrino are in the same family, so again they cancel. So this is an interaction we definitely want to put on our radar. I would say this is assessment worthy for the IB group. Okay, so make a note of that one. Having said that, so what's the opposite of a beta negative decay? Well, a beta positive decay. So you have a proton here turning into a neutrino. So the up stays the same, the down stays the same. And then we have an up turning into a down. And we can use a lot of the same approaches. So there's the equation, proton turning into a neutron plus an electron plus, but not an electron, plus a positron plus a electron neutrino. Okay, so one more time, a proton turns into a neutron plus a positron plus a electron neutrino. So a couple things to note. The positron down here, note the arrows backwards. Okay. Now, we can conserve all of those values. Maybe I'll just slide this up here a little bit. So if we look at the overall reaction, okay, again, let's look at charge. Proton positive 1, neutron 0, positron positive 1, electron neutrino 0. Passes charge. Go to baryon, same thing. Neutron or proton and neutron each get a 1. Everything else is a lepton, gets a 0. Leptons in the same family, negative 1, positive 1, still checks out. And this is the important stuff, I think. If you can get that, you still have to follow these rules, then these diagrams make a tremendous amount of sense. If you zoom in just on, let me grab my green marker here, find my mouse. If you just zoom in on this piece too, and think about what's happening. Well, an up quark has a charge of 2/3. Well, the down quark has a charge of negative 1/3. So if you were to balance this, 2/3, negative 1/3, you would need a +1 to balance both sides. Well, what do you notice? It's a W plus boson this time instead of a W negative. And if you go through, why isn't this guy an anti, for example, versus this guy is an anti? Okay, again, it's to balance those lepton numbers. So it makes a lot of sense if you understand the conservation rules, and you can check whether your work balance is off nicely. This is just a question that I just went over. So here's the the Feynman diagram below represents a beta negative decay. So the down quark is negative 1/3 for charge. The up quark is positive 2/3. The only way to balance that is if this is a negative 1 on the squiggly here. This has to be a negative 1. Okay, and so that's how we know it's a W minus. Okay, the exchange part on this weak interaction is a vertical particle. Okay, so a virtual particle is a particle that has a very short range of influence. And whether it's a W plus, W minus, or Z0. So a Z0 would have no charge. This is negative 1. This is positive 1. All right. I'm not going to read this to you. In the notes that are posted on the PDF, I put in a bunch more stuff for you to read at your leisure. But you do need to know the beta negative decay process really well. You need to know the beta positive decay process really well. Let me just bring this up. So negative has an electron and an anti-neutrino. Beta positive has a positron, which is an anti-electron and a regular neutrino. You got to know that part. Okay, and then there's more on gamma. You can read about gamma. There's more on the strong force. Talks about pions, which are the force carriers, names for the gluons that are doing the exchange. There's something called color. I'm not going to go into color. Okay, it's not an IB requirement. So this is all posted in the notes for people who are really interested. There's further reading on color. This is all posted. And oops, went the wrong way, sorry. There's also a conservation of strangeness, which you can dive into. And there's a really long worked example for those people who are keen. Okay, and then on the last page, this is worth looking at. You can look at these 3 reactions and then try and draw them yourself. So if you want, you can cover them up. Try and draw the reaction yourself and see how well you do. And then you can check your answer here. All right, thank you. Have a good day.